Hello, this is E637. I'm Charles Bouman, and today we're going to start covering more of the material from color imaging and human visual modeling. I think we're really going to start with the achromatic material. So we'll launch right into it. I already started talking about some of this last time, but I'll review it quickly. Okay, so first of all, we're going to learn about contrast and understand the photometric properties of the physical world, and then we're going to understand the percept of color. Last time, hopefully, I convinced you that color is in fact a percept rather than a physical property of a material. Okay, and learn how to use this understanding to design imaging systems. Okay, so the eye. Let's see, the eye. A lot of what I'm going to, in this class, I obviously have to make compromises, or I believe I have to make compromises, because I can't cover everything in total depth, right? So, with MRI, we had very simplified physical models, and here we're going to have similar things, but I at least want to give you some sort of flavor, and then we're really going to focus in on what I consider to be the signal processing aspects of the problem. So, here, this is an eye diagram. There's a lens. There's the iris, which controls the aperture. Cornea protects the lens, and then there's a fovea. There's a retina. The retina is like the imaging plane array. Okay. There's a fovea that's high resolution, and then there's an optic nerve where the signal basically goes out. But the optic nerve actually has causes a blind spot, because in that location you really don't have a high density of receptors. So you basically have a blind spot. Now, I think this is a perfect example of the fact that you have to be very careful about introspection in thinking about how humans respond to stimuli. Okay, because you have a sense of how you're doing things or how you're responding to your environment. But often that sense is an illusion, okay? You feel like you have a certain response, but your real response is not what you think it is. And I think that was perfectly illustrated by that, basically what you might call optical illusions that we had last time. I'm not sure that really describes it correctly. But you had a very strong sense that you were seeing something, but in fact, the underlying physical stimulus was not what you believed it was, right? So, in the case of the fovea, you only really have a high-resolution presentation of the world that's of 1 degree. So at 1 degree, it subtends about 1 degree. So you're only seeing a very small, it's like you're looking at the world through a little, a pinhole or something, But you have this perception that you're seeing everything in the room about you, because your brain basically kind of fills in all the missing information and constructs a model of what you believe you're seeing, right? And you're completely unaware of the fact that there's a blind spot. Now you can actually perform an experiment where you make this clear. You can foveate on some particular object, and then something else that's in the blind spot will disappear. But normally, because your eye is moving around, there's so-called saccadic motion of the eye. It moves around. If it stayed still and you fixated the image on the retina, your retina would basically, your retina is only really sensitive to variations spatially and temporally of the stimuli. So if you actually fixated on a static scene, the scene would disappear. You'd basically adapt. So it's a good example of how you have to be very careful when you make inferences about how humans respond to external stimuli. So the visual system, the fovea has two kinds of photosensors. The one is the rods and the other is the cones. The rods are achromatic, so this is at low light levels they become important. So at very low light levels, you can't see colors very effectively, because it's just the rods that are operating. So they have higher signal-to-noise ratio, but you kind of get less information, and I guess that's called a scotopic vision. And a photopic vision is normal situation. That's mostly what we're interested in. When the cones are operating and you have color vision sensitivity. The cones come in 3 different flavors: long, medium, and short. So if you look at the spectrum of light, the spectrum of visible light ranges roughly from 400 nanometers to 700 nanometers. You have some sensitivity beyond 700 nanometers, and some below 400, but that's primarily where you're sensitive to light. Outside of there, light, this would be below, so as the wavelength goes down, the frequency goes up. People don't normally talk about light having a frequency. They normally talk about having either a wavelength, or sometimes they'll talk about the wave number. But you can take 1 over the number. So basically, if you take the wavelength and you take the speed of light divided by the wavelength, and that'll give you the frequency. That would be a large number, so normally people don't use that. But in any case, 400 nanometers is the shortest wavelength, and that corresponds, the short wavelengths correspond to blue, and the long wavelengths correspond to red. So, very roughly speaking, okay? So, if you go beyond 400 nanometers to shorter wavelengths, that's called ultraviolet light. And if you go beyond 700 nanometers, that's called infrared. And near infrared is very similar to just normal visible light. It propagates sort of similarly, so but you just can't see it. So you can build a sensor to detect infrared light, and then that can have value, right? So and if you go to far infrared, then it becomes close to the wavelengths associated with basically a black body radiation at normal temperatures. So that's far infrared is where you could be able to detect warm objects. But as the wavelengths get longer, then your ability to focus them becomes more problematic, because the longer wavelength, when you take the lens is the Fourier Transform. So if the wavelength is long, then the number of wavelengths in one aperture becomes smaller, and the resolution goes down. So if you have far infrared imaging, tends to be, the images are blurry. Right. Okay.
Excuse me.
Yeah.
What is a Fourier transform?
Well, because remember we talked about this, that we didn't derive the equations, but if this is a lens, right?
Right.
And this is the imaging plane array, then the signal here, in the sense of the electric field, okay, is the Fourier transform of the electric field here. Okay. Right. So basically, as the wavelength gets longer and longer, then the resolution, the resolution of this lens, the size of the point spread function basically tends to vary with wavelength. Okay, so that's pretty much the deal. Okay, now people tend to call the long, the medium, and the short the red, the green, and the blue cones, but that's not true, okay? Because it turns out if you actually look at the response of each of the photoreceptors. Now, this plot right now is, I don't know if they still have this, but in U.S. News and World, in USA Today, they used to have a plot that they would put in the lower left-hand corner, and it was called a factoid. Okay, it was some kind of strange thing. It would be some number of happy people per vacation event. Okay. You'd be like, well, okay, what's a happy person? What do you mean by And the plot would go up or down or something, and and the units were like, there were no units. It was just like some sort of strange plot, right? So right now, this is kind of what this is. Okay, there are no units. It's like I have no idea what he means. Okay, but just take it for what it is. Okay. We'll be a little more precise later. But right here, this is how sensitive you are as a function. How sensitive a particular cone is as a function of wavelength, okay? So if you measure, let's pretend you're measuring the number of firings of the neuron per unit time or something as a function of the amount of energy, number of photons at that wavelength. or some kind of reasonable measurement, okay, then you see that the curves for red, the long, medium, and short codes are different. But the thing that's interesting and perhaps counterintuitive is that the long and the medium are really quite similar. There's not much difference. The idea that like one is red and the other one is green, I mean, that's silly, right? I mean, it's just the long and the medium. And there's a little bit of difference. So it has to exploit that little bit, your human visual system has to exploit that slight difference in order to be able to discriminate this third dimension. And then the short is quite a bit different. But the short actually is also a little odd because the number of cones you have at the short wavelengths, that's the blue, tends to be lower. So blue's a little different. Okay, so that's kind of how it is. Okay, now that we've talked about that, let's completely forget about color for a while. We're going to just first talk about achromatic human visual system response. And one of the problems with teaching this material is it's kind of a self-referential, you know? There's no place to really start, okay? So I kind of just have to plunge in, and things won't make much sense. But we'll sort of come back, and hopefully it'll all be kind of self-consistent in the end. But you got to have to start somewhere. So the first thing we're going to do is we're going to talk about luminance. Okay, what is luminance? Well, I'm not exactly sure at this point, but we certainly have the concept of wavelength, and we can talk about energy per unit wavelength. So we can talk about the spectrum of the light. So the spectrum of the light is I of lambda, and the total energy in between lambda 1 and lambda 2 is I of lambda times the integral from I1 to I2, okay? So now, I'm being horribly abusive of all the concepts of units here, because I haven't really talked about the units. In practice, depending upon what you're measuring, this thing has to have different kinds of units that would make it meaningful. Like it would have to be like energy in ergs or something per unit stir radian, which is a angular angle, right? Or so it has to be, and there's a lot of, I mean, I could go off and teach like at least a lecture or two on all this, okay? But I don't have time, so let's not worry about it too much. The point is this: I here is proportional to energy. It may also be normalized by other quantities, but it's proportional to energy, and that's very important, okay? Because we're going to see that images normally aren't proportional to the energy. You've done the gamma correction lab already? Yeah, okay. So in the gamma correction lab, you saw that the units of images that go between 0 and 255 are not proportional to energy. That's to say, if the pixel is set at value, I don't know, 10, okay? And then you have another pixel at value 20. And if you measured the output energy coming from the pixel set at 10 and the output energy coming from the pixel set at 20 on, a display that's properly calibrated for a display of that image, then you won't find that the energy coming out at 20 is twice what the energy is at 10. In fact, it'll be closer to the square, okay? So it'll be, I guess, 4 times, right? It'll be closer to 4 times. So it's not those are not linear, but we're assuming here that lambda here is linear as a function of lambda. The I is a function, the energy is a function of wavelength, is a linear, has units which are linear in energy. So if I double the number of photons, I double the energy. Okay, that's important because if you have this is a wall, okay, and over here I have a flashlight. Okay, that's what a flashlight looks like. That's what an old-fashioned flashlight used to look like. The ones that never worked and had D cells in them. Okay, and then, this is the light field, okay? And then I have another flashlight. Okay, and so if I measure the light intensity here in units of energy, if I take this flashlight and I measure the energy, and I take that flashlight, so I have E1, and then I have the flashlight E2, then when I have the flashlight when I turn both flashlights on at the same time, what do you think the energy is? It's the sum. Now, why is that? Because the photon energies add. Why is that? Because the phase of this light source are not coherent. If this was coherent light, if it was like a laser, and they were coherently related, then you'd have the electromagnetic field would add, and you would get, diffraction fringes. But because the light is not coherent, it's like if you had two, we learned about random processes, right? So if X is a random process and its power spectrum is S sub X of e to the j omega, right? And Y is a random process and its power spectrum is S of Y of e to the j omega. And if they're independent random processes and I add them together and I get X plus Y equals Z, then the power spectrum of Z is going to be equal to the power spectrum of X plus the power spectrum of Y. Okay? Oh, I went off. That is easily shown because when you take the expectation of the square, the cross term goes to 0 because they're independent. So the same thing's happening with light. When the phase of the light when these are non-coherently related, and the phases of the light are independent, and the average energy you measure here is the sum of the energy. Of course, conservation of energy always holds, but when you have coherent light sources, it gets more complicated. And but what definitely is true is at every point the electric fields add as vectors if you have coherent sources of light, okay? So it's very important for physical reasons that we have the units that we talk about being energy, because that's the relevant quantity. And the reason it is that when we take the lens and we focus it on the surface, okay, that if we have some kind of blurring effect, so we have a point source here, and it kind of gets blurred out. When it gets blurred out in energy. So basically, any filter here, the filter is in energy. Okay, so actually, at the beginning of the course, I told you something. It wasn't entirely true, okay? I told you that if you didn't know the answer to a question, the good answers to the question would be 0, okay? I told you another good answer is 1, okay? If you don't know that, 2 pi is often correct, okay? But from this point forward in the course, if you have no idea what the answer to a question is, a good shot is energy. Just say energy, and you're pretty much, it's worth a try, okay? Okay, so okay, 0, 1, 2 pi in energy, okay? Now, so when these photons add together, what units they add together in? All together? Energy. Good, great. See, I knew you guys had it in you. Okay, good. All right. So that's going to be very important. If you use the wrong units, you'll just get nonsense, okay? All right. Blah, 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 blah. Okay, so, we're not finished here. Okay, so what happens is there's this thing Y. Of course, we have no idea what Y is, but don't worry about that for the moment, okay? So Y is going to be sort of your aggregate response to the light, okay? Everybody has, you see, these days you don't have to worry about this, but when I was young, we didn't have color TVs. And I don't know, we had to actually walk uphill both ways to school, too. But we didn't have color TVs. It was horrible, okay? It was sad, okay? But we had to watch cartoons on black and white TVs. Oh, it's terrible. Okay, anyway, so we all have this concept of black and white. I mean, it's like, okay, so you just take the color out, okay? I'm not exactly, how do you do that? Well, it's actually a very good question. It's not clear, okay? But nonetheless, it seems reasonable. And you could take this I, the light field, and you can multiply it by some y of lambda, which is the weighting, you're more sensitive in the center of the wavelengths, because as you get towards the edges, your sensitivity drops. And you integrate that, and that's the brightness at each point, a single number between 0 and something, okay? It's got to be positive, because the light field's positive, and this response curve is positive, okay? And there's going to be some kind of function, and later on we'll figure out how to actually come up with this function. At least, there are definitely lots of issues here, okay? It's even not going to be a completely simple-ass issue, but at least there's some standard definitions for how to arrive at that function, okay? Okay, now I'm not really an experimentalist, so I can't actually do any experiments, but that's okay, because we can have what Albert Einstein referred to. Are there any German students in the room? I think we have at least one German student. We can have, and they love it when I say this, I must say it really badly, okay? We can have a Gedanken experiment, okay? Oh, is that okay? Okay. Oh, good. That's the best response I ever got. Okay, a Gedanken experiment. What's a Gedanken experiment? It's when you save the time, energy, and money of actually performing the experiment, and you just think about what would happen. And it's intuitively obvious what the answer must be, okay? Okay, so in the Gedanken experiment, we have the following, we imagine the following thing, okay? We have a single dot of some luminance, okay, say 10, okay, oh no, I'm sorry, it's 10 degrees. So a sub 10 is 10 degrees. So the dot is sufficiently large that we have no difficulty seeing it, okay? And it's a uniform background, okay? A large uniform background. So the background is y sub b, and the foreground is y, okay? And we ask the following question. So delta y is equal to y minus y sub b. So that's the difference in the luminance of the two things, right? And the question is, well, if this change is extraordinarily small, then you could imagine that below some level you can't see it anymore. The dot disappears. It's just not visible. Okay? So you can ask yourself, well, how much of this delta y is necessary in order to be able to see this dot? Okay. So, okay. Now, we can get into a lot of fancy discussions and so forth, and, in fact, they'd be quite valid, okay, because, as I discussed last time, when you have probably a false alarm, probably misdetection, you can always detect something with 100% accuracy. All you have to do is always say it's there. The problem is you'll have a lot of false alarms, okay? You'll have all false alarms, okay? So somehow you have to balance that. But you can do that. You can come up with some kind of reasonable criteria, okay? And then you can ask the question, when are you going to be able to detect that dot with the 50% accuracy, okay? 50% of the time. So properly formulated, you can come up with the criteria, okay? And that point at which you can just notice the dot, you're right between the point where you can notice it, where you can see it, and when you can't. Right in that in-between state, that's called the just noticeable difference. So the value of delta y that achieves that point where you just in between, it's sort of like the Twilight Zone. I don't know if anybody watches the Twilight Zone anymore, that place between daylight and night, okay, dusk, okay, when you're just barely aware of what's going on. That's the just noticeable difference, okay? Okay, now, very important concept. So, experimentally, you can measure that. So now you can have the following experiment, okay? First, imagine the following Gedanken experiment. Okay, so you have a uniformly illuminated white board in an otherwise dark room, okay? The background, there's some kind of units here. So the background is 1, and y is 1.1, whatever it is, in some kind of units. So it's a dark room, okay? So, but the board is illuminated, and so this is a 10% difference in the brightness of the dot versus the background, okay? So delta y, j, and d is 0.1 in this case, 0.1 of some kind of units. Now, you can imagine that you can see the dot, because it's a 10% variation in brightness, and 10% seems like a pretty substantial increase in brightness, right? So if the illumination of the paper or the whiteboard is bright enough to be able to see reasonably well, then you would expect to be able to see this 10% variation in brightness, right? Now, the thing is this: you're in a dark room with the lights down low, and you can see the piece of paper just fine. But you're adapted to the dark room, right? Now you take that piece of paper out into bright sunshine, okay? And somehow, so the piece of paper now is so that the background of the piece of paper, see, if I take a piece of white paper, like this piece of white paper. I'll take another piece of white paper. Hold on. You take this piece of white paper, okay? Inside of this room indoors, the amount of light coming on this measured in units of energy is something. Let's call it 1, okay? If I take the same piece of paper out on a bright sunny day, the amount of energy being reflected from this piece of paper could be 100, 1,000 times larger. I mean, it still looks like a white piece of paper, but the amount of light coming off of it is vastly different, okay? Now, you take my word for it. I mean, you could actually go out with a spectrophotometer and actually measure, or you could get a photodiode, and you can measure the amount of light bouncing off of it on a bright sunny day. But the sun is pretty bright. That's why when you're inside a room and you're adapted to the dark room and you walk outside, all of a sudden you're blinded, right? And it's like, oh my gosh. And you have to put on sunglasses and cover your eyes, right? So there's a huge variation, but then the iris stops down, the aperture goes down, and also your retina adapts to the higher photon flux level. Right? That's why it takes a little bit of time for you to get used to the bright sunshine. Okay, so now when you go outside, the background piece of paper could be 1,000 times brighter. Now, if you had some control of, somehow you could control that little patch through some kind of electronic mechanism in your Gedanken experiment, and you could adjust it so instead of it being 10% higher, it's not now 1,100 in the dot, it's a 1,000 plus 0.1, okay? Now, do you think you're going to be able to see that? The variation there is 1 part in 10,000, which is 0.01%, okay? Not 1%, 0.01%, okay? Do you think you're going to be able to see a 0.01% variation in brightness? So you're going to be able to see the dot? No, it defies reason to imagine that you'd be able to do that, right? So what does this tell you? It tells you that just through this thought experiment, that the value of delta JND, delta Y, J, and D. The value of delta Y, J, and D in science and engineering, one very important concept is the concept of an invariant, right? Something that doesn't change. If things change all the time in random ways, then it's difficult to assign any meaning to them, right? So you can define this concept of delta J and D, but if it's always going to be different, then it's not very interesting. So the question you ask yourself is this going to vary based upon the background value of Y? And the answer is yes, because when this was 1,000 times larger, you would certainly expect the value of delta Y, J, and D to become larger. So the question you have to ask yourself is, what is this value going to be a function of? How is it going to depend? What is it going to depend on? Is it going to depend on the person? Hopefully it won't depend on the person. If it depends on the person, if we had to have a different value for every person, well, then that's not too useful. Is it going to depend on the brightness of the background? What else is it going to depend on? Is it going to depend on what you ate for lunch? Right? If it depends on what you ate for lunch, then it's not terribly useful, okay? Okay, so Now, at this point, whenever we need an invariant, it's important to bring some law into play, okay? So somebody has to define a law. So in this case, it's Weber's law. So we have this concept of Weber's contrast. So what we do is, clearly delta y, j, and d is not an invariant. But if you normalize delta y to yb, and you ask this is now called contrast. Contrast is defined as the ratio between the change in something and its original value, okay? And if the contrast that produces a just noticeable difference, the contrast that produces a just noticeable difference is the just noticeable contrast, okay? And now we're going to define another thing, which is if we take the reciprocal of we take 1 over the contrast that's just noticeable difference. This is called the contrast sensitivity. So now let's think about that a little bit. If you're very sensitive to something, then a very small change in contrast will be noticeable. So if you're very sensitive, you might be able to pick up a 1% variation in something, or a 0.1% variation. If you're insensitive, maybe you will not be able to pick up a 10% or a 30% variation, right? So the larger the value of the just noticeable difference in contrast, the less sensitive you are. So they have an inverse relationship. That's why this is called sensitivity. Okay. Now, Weber's law says that to the first order, the contrast sensitivity is approximately independent of the background luminance. So if you increase or decrease the background luminance, the contrast sensitivity stays the same. It's a fixed constant. Okay. Now, in practice, that's not exactly true. So what this theoretically says, the concept is that if you're going to be sensitive to a 1% change, then you'll be sensitive to 1% change independently of what the background lighting is. Okay? So as long as everything scales up proportionately, it's pretty much the same. Now that's not really true, because what happens is that it gets darker and darker and darker and darker. So if you have, one photon, and then you have 2 photons, okay? Trying to see the contrast between 2 photons and 1 photon, that might be hard, because it's just basically dark, okay? So if this is true in anybody here ever designed an electronic system? How many people here have actually physically built hardware to detect anything ever in their lives? Okay, like an amplifier, right? Oh, good. Like for a receiver in a receiver, okay? I mean, what happens is if the signal gets too low, you just get down in the mud, okay? There's just some kind of noise floor to the system. And here's what happened. You hit the noise floor of the visual system. The detectors in your retina, the cones, can only detect so small a signal. And once they get too small, it's just noise, right? There's some background level of noise. In CCD detectors, if you have like a telescope and you're trying to look at distant planets or stars or whatever, then you cool the CCD to lower the background level of noise. But there's always some noise floor. So when you get down into the very, very, very low light levels, the sensitivity is going to drop off just because it's black, okay? Now at the other level, if you have the signal go up and up and up and up and up and up, right? Well, what's going to happen here, this is what happens when you are driving during the middle of the night and someone's got their high beams on directly in your eyes, okay? I mean, you're blinded. You can't see anything. The sensor's saturated. You hit a nonlinear regime. That's as far as you can go. You're outside of the realm where Weber's law applies. So here you're blinded by the light being too bright. Here you're down in the mud where the signal's too small. But in this region here, Weber's law holds. Now, mostly we don't care too much about this because usually we don't have to deal in electrical engineering systems with things that are too bright. It's not like the display, you're going to have to, I was blinded by my display today. I had to put on my sunglasses, okay? That doesn't happen too often, okay? Maybe someday in the future, but we don't. That's not a problem we have today. But over here, you could have this problem where it's too dark. Okay. Now, let's see. So, okay. Okay. So the problem is that y is an energy. Y is units of energy. Remember that. So if I double y, the amount of energy doubles. But the problem is delta y is not always equally noticeable. It depends, because it depends, different delta y, the same delta y can produce different amounts of noticeability depending upon what the background level of light is. Because you tend to be sensitive to contrast, okay? So the problem is this. If we take an image, right? If this is units of energy, and what we did is this, okay? And we use a standard quantization with steps like this until we get to the top here. This is like 0 to 255 because we say have 8 bits. Well, here it's 0, right? When we go from 0 to 1, how much contrast increases that?
A lot.
A lot, okay? I mean, depending upon how you want to define it, you might say it's infinite, okay? If you want to normalize by the mean between it, it's still in that 100% contrast difference. I mean, no matter what it is, it's a lot of contrast difference, okay? But over here, when I go from, say, 254 to 255, what's the difference there? It's small, right? So my point is this: if this is y, okay, and you quantize, if you take y and you quantize it directly, some of these quantization steps represent huge jumps in contrast down at the dark regions. This is dark. And some of them represent very small changes in contrast at the large regions. That's not good. Why? Any thoughts why this is not good?
Because of Mach band.
You can get contouring in the image, right? So let's say I have an image. Let's say over here it's white, and over here it's black, right? So, or let me do it the other way around. Black, and I'll make this white. So I go from black to white. So over here, I'm going to see contours over here in the black region because these little quantization steps represent huge changes in contrast. But over here, I've got too many quantization steps. So I'm not allocating the spacing between these units uniformly. It's important to pick a coordinate system for the data where the fixed amounts of change represent fixed amount of perceptual variation. You want a perceptually uniform coordinate system because when you quantize in a perceptually uniform coordinate system, all the quantization steps are even. You've evenly distributed the resource of quantization rather than concentrating it all in one spot, okay? So if you quantize, okay, one of the things that I'm going to insist that you know when you graduate from this class, okay, is that if you never quantize images in linear energy coordinates. Because if you do, what's going to happen? You can just memorize this response. It'll be actually useful in the exam. So what will happen if you quantize an image? If you take the image, you take it, you see, here you have a CCD sensor, right? The output of a CCD sensor is linear in energy. The actual op-amp, this goes into an op-amp, and the output of this op-amp is proportional to energy plus a constant associated with things like the dark current and the background noise. But it's linear with energy, the output of this op-amp. If I take that signal, I put it into an A to D converter that's 8 bits, what's going to happen? And I try to display that image. What's going to happen? I'm going to get quantization artifacts. And where will I see the quantization artifacts? In the shadows, in the dark regions. Why? Because the contrast changes here are huge. So never, ever, 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 ever do that, okay? We'll talk about that some more. So the question is, if I'm not supposed to do that, what should I do? Well, I need to find some nonlinear transformation of the value y to some other coordinate system I'll call L, where quantization in L is more uniform, where it represents uniform steps in brightness, okay? And not brightness, but in contrast. So I can solve a differential equation to find that. So I want delta L to represent fixed amounts of contrast. So the contrast, I want each delta L to represent one contrast unit of just noticeable difference. Okay. So if I take delta y over y, this is by definition what the contrast is. Okay. So I want this to be true. So what I can do is I can take the limit as delta L and delta y go to 0 and call that dy. So I have that dl is equal to dy over y. And then I can integrate that and I get the following relationship, that L is equal to the log of y. So if I take the log of y, then fixed steps in L represent fixed amount of contrast in y. And that makes sense. By the way, almost any human stimulus, they normally take its log. I mean, think about it. I don't know how much you know about audio, but in audio, you always use decibels. Decibels were named after Alexander Graham Bell, right? And so you take decibels. When you take decibels, how do you do that? You take, say, 20 times the log of the signal if it's pressure, okay? And you take, P. And you take 10 times the log if it's energy. Because the idea is the energy is a square of the pressure, so so you absorb that in this factor of 2. So so that's why people always take logs of human perceptual responses, because the same argument can be made of just about anything that a human perceives, that it tends to be related to contrast. It's always normalized to the background level of stimulus. So so therefore, by taking the log, you put it in units where fixed changes, quantization here represents fixed levels of contrast. Now the problem is that now this is not a perfect solution. There's a few issues. First of all, what goes wrong? Well, if y is 0, you got a big problem. Now you might say, well, it's never perfectly 0. But hey, that's kind of a hassle to have to deal with that, because if you have 0 here, log of 0 is not defined. But actually what's a more problem is that, well, the whole thing with Weber's law was, well, I mean, it's, yeah, sure, I mean, yeah, it's true to some degree, but it's not perfect. Down here, we're getting carried away. I mean, we don't really believe that the difference between one photon and two photons is the same thing as the difference between, a sort of a light a piece of paper here and then something twice as bright. So a factor of 2 at a bright area within the normal range of your visual sensitivity is going to be very different than something that is very, very, very dark. Okay. So here you have to say, well, I don't really believe Weber's law that much. Somehow I have to tone it down a bit. Okay. So a standard way of fixing this up. So this just says, okay, there's some problems with Weber's law. I mean, it's like anything else. It's true up to a point, but you have to be pragmatic about it a little bit. You have to make some adjustments. So the way people normally make adjustments, the simplest thing to do is what they call Powerlaw Contrast. Okay, and you just say, okay, well, what I'm going to do is this. I'll say, okay, before I said that the just noticeable distance L was delta y over y, but now I'm going to multiply it by y to the p, because I'm going to say, well, let me see. The contrast will get larger. The just noticeable contrast will get larger at low values of y. Okay, so by multiplying this by p, I'm going to divide it. This has to get smaller, I think. Hold on. It always takes me a while to remember it. So this has to be equal to the just noticeable contrast, okay, times y to the p is equal to delta L. So the just noticeable contrast, oh gosh, I always have to go through this fairly carefully. But p here is less than 1, okay? So the function y to the p, if you have y to the say 1/3, then it's like taking a cube root but putting it on its side, right? So it would be like if you turned it this way, well, you'd have to flip it also, but it would be like a cube function. So you have a function like this. So what it's saying is that the delta L has to be larger at dark. Right. Yeah, let me see. I always have to remember how this works. So the delta. Oh yeah. So the delta L has to be. So the just noticeable contrast has to be larger at smaller values of y. Right. That's correct. Anyway, you integrate the equation and you get this. You get that the contrast sensitivity, which is 1 over the just noticeable contrast, is going to be equal to 1 over delta L times y to the p. And then you integrate that, and you get that you get delta L dl equals dy over y times 1 minus over y to the 1 minus p, and you integrate that, and you get L equals y to the p. So in the limit as p goes to 0, the behavior of L equals y to the p behaves like log y. And the smaller you make p, the closer you have to something that approximates Weber's law. So if you really believe Weber's law, you want to make p very small. If you don't believe it so much, you make p larger. So it's sort of a practical trade-off, too. Another factor is that what happens is that this function, its derivative, becomes very large at 0. It's very steep. So if it's very steep, if you have a slight miscalibration in terms of the input signal, then you can get massive changes in the value. So it becomes very sensitive. So that's also sort of a practical consideration. And so what happens is that the standard solution is what's current. Typically, in image compression or image file formats, when you download an image off the web, p is equal to 1 over 2.2, okay? But when you're trying to do like experiments where you're trying to measure human visual system properties, if you're talking about like a scientific application, people typically assume p is equal to 1 over 3. So this is more accurate, okay? But the problem is the slope becomes very steep, and it's like, particularly in the early days before they had computers and everything was digital, the analog systems could drift, and what they standardized was pretty much on this. So this is kind of the standard for actual practical application. This is the value that's typically used in sort of psychophysical experiments. So just to summarize, here you have, the so-called gamma correction, the value of gamma that's used in NTSC video, and we'll talk about gamma correction next time, is 1 over 2.2. In sRGB, it's 1 over 2.2. Standard PCs and Unix, 1 over 2.2. It used to be a long time ago that Macs used 1 over 1.8 because they felt like they had to be different, okay? But finally they gave in, and now they're using 1 over 2.2 also. And in LAB, which is a color space we'll talk about later, they effectively use 1/3. So that's pretty much it. We're out of time now. So are we out of time? Yeah, we're out of time, aren't we? Oh, usually they go off. Oh, there we go. Hey, I was paying more attention than you guys.